Our last speaker for this morning session is Professor Sabir Guseyn-Zade from Moscow University, and he'll talk about the variants of the exotic configuration spaces via the power structure over the Grothendieck varieties.
Well, thank you very much for giving me a possibility to give a talk here. So I'm really happy because for a long period, especially when I was a student of Sergei Petrovich Novikov, I mean real student before becoming a PhD student, I was under very deep influence of Viktor Matveevich. Later also, but on that period it was direct influence, and I probably can comment more, but I have no time for that. So my talk will be about some generalizations of classical configuration spaces, which are the main examples, the simplest examples of configuration spaces, which I want to discuss, and which give examples of the equations around them, are the following ones. First of all, this if you have a topological space X, one has the symmetric power of X, which is X in the power n factorized by Sn. This is one example, and another example is the space what is usually called configuration space of X, which means configuration space of n tuples of different points in X. Here you have, in principle, points can coincide, of course. So you take X in the power n minus delta, where delta is the big diagonal, the set of n tuples where at least two elements coincide, and this is factorized by Sn. So first of all, there are classical equations for generating series of the Euler characteristics of these spaces. No, of course, Euler characteristic is defined only if spaces are nice enough. And say, I'll have in mind, say, unions of cells in finite CW complexes as examples of spaces where everything is defined. And of course, this is rather general. Many spaces can be represented like that. And the classical McDonald equation says that, let us write 1 plus sum for Q from 1 to infinity, Euler characteristic of Sn x, t in the power n is equal, maybe I write and then tell something, 1 minus t in the power minus Euler characteristic of x. Here by the Euler characteristic, I mean not the homotopy invariant Euler characteristic, which is usually, say, defined in courses in algebraic geometry, but the additive Euler characteristic, which is defined through the, for example, as alternating sum of the ranks of cohomology groups with compact support. Then it is additive one, and one has equation like that. It is McDonald equation follows from computation of McDonald's of homologies of Bethe numbers of symmetric powers, and in fact, it is a sort of a very elementary one. For this, there is also something very similar. One has equation like that: 1 plus sum for Q from 1 to infinity. I could write even without 1 because simply writing for Q from 0 to infinity, but doesn't matter. Euler characteristic of this x is t in the power n is equal to 1 plus t in the power Euler characteristic of x. So somewhat similar for equation. Now the Euler characteristic is the only additive and multiplicative automatically, but it's not so important for that. Excuse me. Invariant, topological invariant of spaces. But if one works with spaces with additional structures, then there are some other additive invariants, in some sense generalized Euler characteristics. And for example, there is, if one considers quasi-projective varieties, if X is a quasi-projective variety, this means a projective variety minus a projective variety. Then there are other ones. for example, one of the most complicated invariant is the Hodge-Deligne polynomial of x. So one has the following polynomial: ex of uv is a polynomial in two variables. For any quasi-projective variety x, it is defined. And there are different definitions, but the simplest one, which of course does not guarantee, is somehow substitution of method of computation of it, is the following one: that if y is Zariski closed, so it is defined by the following two properties, this polynomial. If y is Zariski closed in x, that means that y is defined by additional equations in the projective space. Then ex of uv is equal to ey of uv plus ex minus y of uv. The additivity of this polynomial, which is, I told you that this Euler characteristic, which is defined through cohomology groups with compact support, is additive, and the additivity means just the same. Euler characteristic of x is Euler characteristic of y plus Euler characteristic of x minus y. Here is an analog of this. And there is normalization of it. It means the following: that if x is a projective manifold, so this manifold is smooth, projective, compact, projective, then ex of uv is nothing else but sum over all p and q. One takes the Hodge numbers, HPQ of x, dimensions of the cohomology groups represented by, there is Hodge structure on the cohomology, and these are dimensions of this, times minus 1 in the power p plus q, u in the power p, v in the power q. So for smooth manifolds, it is essentially like that. It is very easy to understand that these two properties define the Hodge-Deligne polynomial. Deligne is because Deligne proved that there exists extension of these numbers to, also with extension of the Hodge structure on the cohomology group to singular manifolds, or non-projective, singular or non-compact manifolds, quasi-projective. This is achievement of Deligne. Because of that, there is this is Hodge-Deligne, and the extent of Hodge structure for this case when x is either singular or not compact or both, one has a mixed Hodge structure on that, but this is not essential. And then, for example, this invariant, one can write a sort of equation like that. But in order to give sense to this equation, it's a little bit tricky. It's like that. I'll write, for example, only for that. It's 1 plus sum for q from 1 to infinity. Hodge-Deligne polynomial of x, of s and x. We take symmetric powers. Symmetric powers of a quasi-projective varieties are also with quasi-projective varieties of uv times t in the power n, y. What did I write here? Nobody corrected me. It means that nobody tries to watch me. This is how to say it. When I give lectures to students, if I make a mistake like that, I usually say that I made this mistake intentionally in order to check that students try to follow me. And if nobody notices this, doesn't it? There are more? Oh, a lot of I tried to skip. So there is one who at least followed, but now people want to correct me more. No, this seems to be now here. I had started to check to correct this, but okay. That this is one can write 1 minus t in the power minus minus this Hodge-Deli polynomial of uv, but in some sense, so I have to write like that in quotation marks, where this means the following. This is relation. This is why this is denoted by that. I don't want to make to comment at the moment. Maybe I'll comment a little bit later. But this is defined like that. That 1 minus t in the power minus a u in the power p v in the power q. So when you write an equation like that, of course you mean that if here is a polynomial, to define this value, this series, you need only to define it for monomials, because for, the polynomial is sum of monomials, and 1 minus t in the power sum of something is product of this. So what you have to define this, and this means the following: that this is 1 minus t u p v q in the power minus a, where now it is everything is defined in the sense that now here is the usual meaning. You have this expression, you have to take it in power minus a. A is an integer number, in fact. Maybe it was better to write okay, integer, because all these polynomials are, of course, with integer coefficients. So this is an integer. Okay, this is in some sense the definition of that, let us say, these quotation marks. Now I want to switch to the, so this is not so good. Maybe I'll try, there was one with, okay, I'll try maybe that, maybe it is more visible. Let us try. So now what sort of generalizations of these objects and these equations in some sense I want to discuss. So first of all, about the exotic configuration spaces. What does it mean? One can say that these spaces are, one can say that one marks points, and points can be either considered with some multiplicities or without multiplicities, only one point, each point with multiplicity 1. This is defined like that. Exotic configuration space, this is a notion introduced at a moment in a little bit not so wide sense, as I discuss a little bit, by Yuli Barishnikov, is the following one. Suppose that one has, say, R colors. R colors. And one considers on a space X, one considers configuration space of points, so that each point can be colored by some of these colors. So suppose that colors are, I don't know, red, blue, and what is green. And in principle, each point can be colored by red, blue, or green with some multiplicities. But some combination of multiplicities are permitted, and some are not permitted. No, what is permitted or what is not permitted is defined by a certain set. Let us let z in the power r greater or equal than 0, maybe better to write like that, be the lattice, the positive part, the non-negative part of the lattice of dimension r, and we take without a certain subset in it in the complement to 0. This is this set is the set of permittable multiplicities for different colors. So each point here is defined by R numbers, multiplicities of colors of each color, and the I can be some points are, some combinations are permitted, some are not. Now, for example, SNX is defined like that. In this case, that R is equal to 1, you have only one color, and all possible all possible, this is 0. So 1 is permitted to the set I is the set of non-negative numbers. All multiplicities are permitted. And this configuration space means that, again, I is equal to 1, but only I is consists of 1 point. Only points of multiplicity 1 are permitted, nothing else. So this is that. And other examples can be that I, for example, is an arbitrary 1. But if you take a point k equal to k1, etc., kr inside z greater or equal than 0 in the power r. For example, one can demand that the sum of all multiplicities, the sum of all colors is bounded. So one can take, for example, I is the set of this k such that absolute value of k, it means k1 plus etc. kr is less or equal than fixed m. Or, for example, another example, I is an arbitrary, but the set I consists of only of points on the axis, nothing else. In some sense, this means that each point can be taken with any multiplicity, but different colors. I of course made a quick picture for I equal to 2, but can be arbitrary. But points, different colors can be met at one and the same point. This is this set. This example was called by Baryshnikov was called an apartheid configuration space because all of them are not permitted. So in fact, I want to discuss a little bit. So I want to discuss analogs of these equations and even more general than this one in the case of exotic configuration spaces. First about the Euler characteristics. So this is first of all analog of this equation. It is very simple one, and in fact the proof is absolutely elementary. And I mean more simple than one can imagine from and in fact it's strange that this equation initially emerged from rather sophisticated computations of McDonald's, not directly. The answer is the following one. I want to write the following, let it be 1 plus sum for k in, of course, I forgot to say that each configuration space must be numbered like here, numbered by the total number of points which are participate here. Now we take configuration space, how to is like that. Let it be no configuration, maybe conf. Okay, f I, the set of permittable combinations, and here you can have to put n bar. N bar means maybe he was q, but from time to time, at the moment there was also n. Q was n here, so I prefer maybe n. N is n1, etc. nk, and here you mean that each point, the sum of colors, the sum of multiplicities of all the points, multiplicities corresponding to the color are. To this color, to the first color is n1, to the last color is nr. So this is of x. So, for example, here you can consider conf for this I, k n1, n2 of x, and this means that you take some points. Some points are colored by the first color with total multiplicity n1. Some points are colored by another color with total multiplicity n2, and points of different colors cannot be met together. So this is this configuration space. So k is in z greater or equal than 0 in the power r minus 0, and now better to write because I'm changing notations. Euler characteristic of conf I n of x T bar in, this is bad. I have, maybe it's better to erase this. Where is it? Ah, here it is. T bar, T underlined, N. Sometimes I put over, sometimes under, doesn't matter. Where this means T1 in the power N1, etc., TR in the power NR. So you take the generating series, but of course in R variables, because the spaces are numbered by R tuples of numbers. So the equation is like that. Let us consider the following simple series. One simply takes the sum over all n in I. You take only theirs which are in I. T, okay, I put underline, I put here also, in the power n. So you simply take the series where the monomials corresponding to a permittable combination are with coefficients 1, and monomials with non-permit combinations with 0, with the number 0. And you put here, in fact, simply Euler characteristic of x. Very simple equation. So here, what is why this is the same? So in this situation, the permittable points are like that, and because of that, this series is nothing else but 1 plus t squared plus t cubed plus etc. Because you take sum of all them, and of course you have this is 1 minus t in the power minus 1. And this is the particular case of that. And here it is 1 plus t, nothing else. 1 plus this t. So the equation is very simple. And in fact, the proof is even more simple than the equation itself because of the following. When one looks at this equation, let us denote its left-hand side by zeta x. No, I, somewhere I have to put I of t. Why zeta? It is related with some zeta functions, but I don't want to discuss this because of that. Also, it's related with so-called Kapranov zeta function. And then it is easy to understand that one has the following property, which substitutes this additivity property for that. It is like that zeta x of, no, I have to write all the time, of t is, if y is inside x, like here, then one has the following, that this is zeta y I of t times zeta x minus y I of t. And this follows simply because of the following. If you have to consider some sets of points in x which have total multiplicity n, you can take some of them are in y and some of them are x minus y. So you have to write that this space is disjoint union of products of those corresponding to some in x and some in y, and then you write down, and this is obvious an obvious equation. And then in order to prove it for spaces which I wanted to discuss, very general in fact objects, unions of cells in finite CW complexes, you can have to write to prove this equation only for cells, because each space is union of cells, the joint union of cells. And for a cell, you can go like that. For cell of dimension 0, this is obvious, because when you take cell of dimension 0 is nothing else but 1 point. And if you take 1 point, then of course these configuration spaces consist only also of either of 1 point in the case when the corresponding coloring is permitted, or 0 points. So it is nothing else but this series for 1 point. And all characteristic is 1, of course. Now, if you take the cell of dimension 1, a cell of dimension 1 can be represented as union of 2 cells of dimension 1 and 1 cell of dimension 0. And then, of course, zeta, well, shall not write I, sigma 1 of t is zeta sigma 1 of t squared, according to this multiplicity, times zeta sigma 0 of t, t underlined. So, and of course, this means that sigma zeta sigma 1 of t is nothing else but zeta sigma 0 of t in the power -1. But this, of course, is just the same equation because the Euler characteristic of cell of dimension 1 is -1. And you can go on like that. So this is very simple and trivial observation. Now I want to move to the but I remember that I have. Okay, now let us move to the situation, something like that. But in fact, I want to write an equation in a more general setting. Namely, the Hodge-Deligne polynomial is an invariant, additive invariant of, but in the class of quasi-projective varieties. But the most general one is so-called universal Euler characteristic of quasi-projective varieties. It means simply the following: it is tautologically universal, and this is just like that. It is the Grothendieck ring of quasi-projective varieties. I work over C. This was, I didn't tell you, but of course this was over C. I told about Hodge numbers and so on, of course. Hodge numbers. And this is nothing else but the group generated by classes of isomorphism or quasi-projective varieties modulo the schizo relation. X, if Y is Zariski closed in X, then a class of X is class of Y plus class of X minus Y. And this is so-called substitution. This is substitution of these equations in the categorically most universal situation. And then it is a ring because simply you write that, I don't know, X1, X2 is defined as the class of X1 times X2. So this is a ring. And quasi-projective means projective minus projective. Quasi-projective means this. Now, this is a very complicated ring, but many computations in it can be made even simpler than, for example, computations with the Hodge-Deligne polynomials or something like that. For example, when it was necessary to prove that Hodge-Deligne polynomial of a Crepant resolution of a certain group quotients in the context of mirror symmetry doesn't depend on this resolution. Kontsevich understood that it was more easy to compute everything, not with Hodge-Deligne polynomials, but in this ring. And this was the origin of so-called motivic integration. And this led to the proof in particular of this mentioned. Now I want to, to explain. So sometimes this is just in the context of motivic integration. This is sometimes denoted by Euler characteristic, generalized Euler characteristic of X, the most generalized Euler characteristic of X, though it is an element of a very complicated ring. And this is the reason. The reason for that is because sometimes, in particular in the context of motivic integration, you need to write something like integral of something with respect to the Euler characteristic, the usual Euler characteristic, or with the generalized one. And with this notation, it is somehow what to put here is not clear. So this is more or less motivated by that or something like that. This is the usual object in Mativik integration. Okay, so now if X is a quasi-projective variety in this context, then all these exotic configuration spaces, which are these ones, they were deleted, these ones, all of them are, no, at least not quasi-projective really, but constructible sets. This means finite unions of quasi-projective varieties. So quasi-projective varieties do not organize an algebra of sets, but to make the minimal algebra which includes all quasi-projective varieties, you have to work with constructible sets. And the equation is, in fact, rather simple. I'll write you what did happen here. What did happen here? No. This is equal to that. I see. Now I see. Of course, the black ones. I want to write a sort of generalization of this equation. And the generalization of this equation is, from formal point of view, an extremely simple one. Namely, it is like that. Let me just to use how to say it, to benefit from the fact that I can use the eraser. Let us write it like that. I'll write here, but the meaning of that has to be defined. And this will be, I'll do that in some minutes, first of all. So I want, instead of the usual Euler characteristic, I want to use this generalized Euler characteristic. That means the class of the variety. So maybe instead of writing he, and even instead of writing he G, generalized one, I'll write like that. I take these configuration spaces, I take their classes, oops, I switch their classes in the Grothendieck ring of varieties here. And I want to write down this series. And in fact, the answer is extremely simple, but it has to be interpreted, because otherwise it is sort of nonsense. You have to put here this series in the power class of X. Class of X is an element of the Grothendieck ring of varieties. Now here he's a sort of degenerate series, because coefficients are either zeros or ones. But nevertheless, I'll define the meaning of that maybe in a little bit more general context, because with the power, with the series downstairs being a more general one. Excuse me, please. Maybe I made it. Maybe I made it. But you see, I always mix this and also mix this. You are right. Okay. So this is the meaning of that is defined by the so-called power structure of the Grothendieck ring of varieties. A power structure of a ring R is a method to give sense to an equation, to a expression like that: 1 plus A1t plus A2t squared plus etc. in the power R, where all AI and R are inside R. So this has to be defined as the series like that, with coefficients in R as well. So that the usual rules of exponential function hold. R may be bad, maybe better. Some R was there used M, just because R was used here for something. Excuse me, please. M. So that the following is, let it be A of t. The following properties must hold: A of t times B of t in the power M is equal, everybody knows, So what is it? It's equal a of t in the power m, like usual. Then a of t in the power m1, m2 is plus m2 is equal also everybody knows. And finally, a of t in the power mn is equal, everybody knows what is it equal to. All the usual rules has to be fulfilled. No, of course, if a is 1, must be 1. If m is 1, it must be this one. I don't write this as a question. And in fact, this construction, when you work with one t, permits easily to define what does mean when you have several t. I simply have some lack of time. No, maybe not. Maybe I even no, of course. So I'll define this expression in the case of varieties. I'll define in the case where AI and M are from this ring. No, I'll define for, in some sense, for I equal to 1. That is when you have only one variable t. Simply to save some time to explain the equation or something like that, because I have a certain lack of time. So this is what does mean this power structure over the varieties. By the way, the Hodge-Deligne polynomial is a homomorphism from K0 to the ring of polynomials in two variables. So if you write an equation for that in K0, you can instantly have an equation for Hodge-Deligne polynomial or something like that, or Poincaré polynomial if you identify U with V. Okay. And no. Its definition is, of course, for definition is yes, but for an arbitrary, who knows what is definition is, of course, for arbitrary, but there are, of course, there is natural power structure over Z. When you take a series and you take in the power, everybody knows how to compute a power, integer power of an integer series with integer coefficients, no problem. But if you have more complicated, for example, even polynomials in two variables, the power structure is a little bit sophisticated. I don't want to. So the equation is like that. Suppose you have a series. One, you take classes of varieties. Class of variety A1, T plus class of variety A2, T squared, plus etc. And you want to put here class of variety M. So A1, A2, and M are quasi-projective varieties. Nothing, so complex varieties. The answer is the following, that this series is 1 plus sum for k from 1 to infinity. So I want to write the coefficient at t in the power, maybe even further, I don't know, t in the power k. Coefficient at t in the power k in this. And the answer is the following, that this is, you have to take sum of all partitions of k. This means a set of ki. Ki should be greater or equal than 0, so that sum of I ki is equal to k. So ki are partitions of k. It means k1 sum is equal to 1, k2 sum is equal to 2, and so on. And here you have to write the following varieties. Classes of the following varieties. You take M. This is a manifold, this quasi-projective variety, in the power sum of ki. You subtract the big diagonal here, which means sum of ki tuples points where at least 2 coincide. Then you multiply this by, what happens? It is on the next level, but okay, I'll put it up in a moment. Then you multiply by product for over product of AI in the power ki, product for I from 1 no, product over I in principle runs from 1 to infinity, but of course for each partition you have only finitely many. And then you have to factorize this. This is a quasi-projective variety, but you have to factorize by the product of SKI, product of the group of permutations on KI elements, which acts. So I tried to put it on the same level, but I made a mistake, of course. And in order to factorize, you have to define the action of SKI here. And the answer is the following. This is contained in the product, this one. In the product of M in the power Ki, M in the power sum of Ki is just this product. And so SKI has to act on this factor, permuting the components of it, permuting this Ki components, and simultaneously on the corresponding factor here, permuting Ki components of AI here. And if you get simultaneous permutation, you have in fact a free action of this, because this free here. And the quotient is, for complex numbers, the quotient is also a quasi-projective variety. And so this is class of quasi-projective variety. I had to put here, I put this bracket, but it is better, no, not better, but reasonable to put this one. I mean, up. You started to be very, you start to prove that you follow all my misprints. Okay, I have to put that one. That's true. So this is the definition. In fact, if M and AI are finite sets, which are particular quasi-projective varieties, this tends to be a standard equation for the powers of. So you have the following, that in calculus or in combinatorics, 1 plus A1 over for integers plus A2t squared plus etc. in the power M is nothing else but 1 plus sum for K from 1 to infinity, sum for Ki, such that for partitions, I don't want to repeat all this. And here you have to write M times M minus 1 times M minus 2, etc. M minus sum of Ki plus 1 multiplied by product of AI in the power Ki, and then divided by product of Ki factorial. No, this is standard equation from, maybe not from books in calculus, but for books in combinatorics, you can find this equation. And if you look here, you can see that if these are finite sets, this is nothing else but the number of elements here. If you take M in this power and throw out the big diagonal, you have this, the number of elements is this one. And factorization by free action of SK is, of course, nothing else but division by Ki factorial with the number of points. So in some sense, this is a sort of obvious generalization of that one. Obvious, no, not obvious, of course, not obvious, by the way. So, in fact, what is about? Hope I have, okay, I have even 3 minutes more. For this, maybe it is even easier to interpret this equation, this relatively, in this case, in the following way. Maybe I can write it like that. So if you have an arbitrary series of this form, let us take this series, then it can be represented in a unique way, like the following product. So I write, excuse me for jumping to that. No, maybe I take this series. And I can write it in a unique way like that. It is product over all m in z greater or equal than 0 in the power r, 1 minus t in the power m in the power minus, let it be sm, sm. S small, it is okay, let it be sigma in order not to mix with that one. So why this, what is this means? So if you have a series like that, you can take, for example, the point 1, 0, 0, 0, and of course, the first polynomial, the first monomial here will be the one in for m equal to 1, 0, 0, 0, and has to coincide either with 1 or 0. Then you divide by it and so on. Sm in principle are integers. Not, you cannot write that they are, say, 0 or 1 or something like that. So you can represent that equation like that. And then if you want to write this one in the power class of x, because it is written here that it has to be in the power of x. And then it is nothing else but, in fact, it is like that. It is 1 plus class S1 of x t in the power m plus, excuse me, product of course over all m like that, 1 plus S1 plus S2x class of S2x t in the power 2 bit I write, okay. So of course I a little bit skipped this fact when there is not one t, but I define that one, so it is in the, one can say that this is independent of that. On that plus etc. You have to take this product and then to put it in the power sigma m. This is integer in this case, in this particular case, and because of that, meaning of this series is somehow obvious. And this gives you another. By the way, to understand, so from that description, it is clear, because these are configuration spaces, it is clear that these are really, the coefficients are constructible sets. They are sums of quasi-projective variety. But if you do like that, in principle, because sigma m can be positive, negative, and so on, from this equation to understand the coefficients are quasi-projective varieties, but not their differences. So in the Grothendieck ring, when you define the Grothendieck rings, you have to add not only you have some operation, you have to add extra. What does mean minus? A minus B, but differences of two classes. But from this to understand that the result is really without differences, but really quasi-projective variety, from this definition, it is, from my point of view, impossible. At least I don't know how to do that. So that's all. I am on time. This is very, how to say, usually I try to be like that. Thank you very much for your attention.
Are there any questions or comments? So this power system, Sabir, that you have.
Power structure.
Oh, power structure. Yeah, that's. I mean, there is a power system in formal group law theory, where you take powers in the formal group law, and is it somehow related to? Do you have some kind of
something related with Adam's operations in something?
Well, yeah, Adam's power operation are particular cases of this power system with the multiplicative formal group law. Yeah,
there are some relations between these objects, this Adam's operation with this notion. I mean that Zhenya Gorsky at the moment described this. There is a paper with Gorsky which describes the sort of relation with power with Adams operation.
Yeah, but this Adams operation of particular cases of this power system, you have multiplicative formal group law. Maybe so. Well, then maybe I try to say it in a different way. Is there some formal group law behind this?
I don't know. I don't know, and I didn't think about that. Maybe Zhenya Gorsky was the one who thought more about this particular situation. I don't know.
Okay.
So my question is, if you consider, when you consider these exotic configuration spaces, you impose some conditions on tuples of points, something like you don't allow coincidence of some points with given colors or so on. What if you impose some geometric conditions on tuples of points? I mean, for instance, you exclude tuples of points which lie in a smaller subvariety or whatever. For instance, if you consider projective space, you may exclude points lying on a hyperplane, whatever. Can you compute these zeta functions in this case?
So the standard answer, a very interesting question, which I didn't have in mind. I never had it in mind. So I have no comments because I didn't think about that, but maybe this can be.
So probably this method could apply also.
It's possible. I don't know. But this is, I really didn't have this, never had this in mind. Even the questions like the previous one I had already, not for the first time. I knew that I have to send to Zhenya Gorsky or something like that. But with this question, I never had it in mind and never, I know nothing.
Thank you.
All right. If there is no more question, let me check maybe that there were some questions in Zoom. Not yet. Okay, well, then we finish our morning session, and we have lunch for a bit more than